Hello, everyone. Welcome to our keynote speaker for day one. This morning we had some great sessions. We had lots of great discussion. And so what better way to kick off the rest of the afternoon with some great insights by Professor Rawal. So to introduce you to him, he is a professor at CEPT University in Ahmedabad, India, and executive director of the Center for Advanced Studies in Building Science and Energy at CEPT Research and Development Foundation. His research and education activities revolve around building envelope optimization, building performance simulation, thermal comfort, and architectural science education. He is the recipient of Jeffery Cook Scholarship by the Society of Building Science Educators and has recently become an ASHRAE Fellow. He is a member of various technical committees with the Bureau of Energy Efficiency, Ministry of Power, Building Certification Institute, India Green Building Council, and the Global Cooling Prize. His work has helped define thermal comfort standards for the Bureau of Indian Standards and helped develop Building Energy Code for the Bureau of Energy Efficiency. He is a founding member of the IBPSA India chapter and also serves as the IBPSA World Education Committee Chair. He has authored numerous research publications and is currently a co-investigator on 2 UK projects worth just under £2 million, entitled Low Energy Cooling and Ventilation for Indian Residences and Grounded Energy Modeling for Equitable Urban Planning Development in the Global South. So it's our great pleasure to have him with us today. You can see his title here on the screen, so I'll let you take it away.
Thank you. Thank you, IBPSA England. Thank you, Bianca, for generous introduction. And good morning, good afternoon, good evening, wherever you are. I will be talking about a little bit about in what context are we functioning and where are we, what we are trying to do and what we need to do as a BPS community, Building Performance Simulation Community. The presentation is titled BPS, that is Building Performance Simulation Without Confirmation Bias, and nuances for non-homogeneous world. So I'll try to deal with what has happened and where we are. So probably my slides seems to be a little stuck. Yeah, probably I might need to do a little bit of back and forth. Seems that connection is not very good. So where are we? We sort of seems to be in a post-industrial world where what matters nowadays is a profit yield is being seen as an analysis. In a pre-industrial world, profit yield used to be extraction of minerals, agriculture. In industrial world, profit yield used to be a fabrication of various machines and so on and so forth. But in a post-industrial world, analysis is what the yield is. And in the economic sector, if you start looking at, as I mentioned, agriculture and mining in a pre-industrial area, industrial era, it was manufacturer. Now the service industry is actually driving the economic world. What are the transformation resources we used to have in pre-industrial era? It used to be wind, water, animals. And fossil fuel has sort of taken over during industrial era, which is coal and electricity. But probably today, as many of you would agree, that information is sort of a resource. It's a data, is a resource. Kind of skills we used to rely earlier was craft, and later on know-how. But probably now the science and design is a kind of skills which everybody look for or try to gain that. Nature was a context in a pre-industrial time, but then it became a resource when it came to industrial time. But now we look for nature as a solution. We try to biomimicry and many other domain areas, subjects. We try to find how can we really learn from nature. And so nature has become a solution for us. Interaction, it used to be between people and nature. Later on, it became people and machine. And now what we are doing is people to people. This is one of the best examples that how are we sort of interacting with each other. Ecologically, nature was abundant in a pre-industrial time. Then we went through pollution and depletion of a lot of resources. And now probably what we are trying to look at is a sustainable way of managing our natural resources. And this is where the building performance simulation community fits. This is where it sits, where we try to service some of the industry. We try to rely on analysis. We try to rely on many of things, which is part of the information technology. And definitely we are sort of looking at design of buildings based on scientific rigor, based on scientific experiments and so on and so forth. So this is what the post-industrial society we are in, and this is where a building performance simulation community sits. Also, I will try to give you a little bit of background in our global context, especially with the building sector. The previous slide was dealing with most of other things, was applied to all kind of sectors, but probably next few slides, I'll try to deal with what happened in terms of global sector. Le Corbusier attempted to deal with many forms of architecture. Same with the Frank Lloyd Wright. I could have named many other modern masters, but probably I picked up these two, trying to make a case that how architecture has evolved in the modern times. And to me, when architecture used to exist earlier also, but when there was a conscious client and consultant relation started getting in, and when people started offering their services to design buildings, this is where the modern architecture started giving certain kind of outputs to the society. So what happened, and I am taking these inspiration from a book called Energy and Memory. Originally was written in a non-English version, but now we have an English version also, and I recommend many of you to read if you have an interest in architecture and how modern architecture took care of some of the climate responsiveness and so on and so forth. So Corbusier's building, where the sun was definitely a guiding factor, but what he dealt with, he probably started responding to the sun in a very regimental, very disciplined manner. And once he managed that, once he started negotiating with the outside world, what all happened inside was all acrobats. He took enough liberty to make spaces within that. Versus another energy source in a Frank Lloyd Wright's building was a fireplace. In a Northern American climate, especially Chicago and the colder areas, the fireplace in a residence became a core of the entire house. And the entire plan emerged out in and around the fireplace. So these are the two separate, very, very different approaches we saw in a modern architecture. Both try to deal with the energy in a manner. So in the same book, the author is saying that to Corbusier, the sun is a luminous and regular sign that normalizes and organizes the life of human beings. To Frank Lloyd Wright, the sun is more than it is light, a beginning more than a regulator, a factor of change rather than a stability. His is a warm, chaotic, igneous sun, a cosmic fire. So both attempted to deal with this climate response, this climate effects, and then try to respond to it in a manner. So energy was became a center of the design, became a generator of the design. Not only the building envelope, but both attempted to deal with energy services or HVAC services. Corbusier attempted to do certain things when he was designing Centro-Soyuz building, which was supposed to be in Russia, and it is, I think. And he attempted to integrate a facade with a certain kind of system so that it provides enough warmth inside the building. He looked at the HVAC system as integrated part of architecture very early on. However, during that Centro-Soyuz building, he could not really demonstrate what he wanted to do that. But when it comes to Salvation Army buildings in France, he attempted to do that, and he successfully demonstrated that. At the same time, Larkin Administration building near New York, Frank Lloyd Wright also started working in integrating HVAC system with the building envelope systems. That was a building probably first time used radiant floors. Unfortunately, we don't have that building now, but that was these are one of the first two attempts where both modern masters have adopted HVAC technology or mechanical means and started integrating that with a building. And the kind of variations which we observed and we are still observing in many of these practices is amazing. The kind of, you can look at the building and immediately you can figure it out probably what climate that would be in. Or you look at the facade and you can figure it out, probably this might be a northern facade or a southern facade in this particular latitude, this particular longitude. So buildings, not only in internal spaces and not only aesthetics, but also start where the examples, where the conscious efforts to respond to outdoor climate and also to integrate a building services depending upon the context, where the example of that. But then later on, for some or other reasons which many of us are aware about, whether you are near to the tropics or you're near to the poles, whether you are in 1 degree north, 29 degree north, or you are up 50 degree north, probably the kind of variations which we would like to see and appreciate, we don't do that. Whether it is a San Francisco or Kuala Lumpur, the kind of buildings which we see do not really provide us any kind of opportunity where we can appreciate the context. Heavy reliance on technology, heavy reliance on only and only mechanical means is where many of these examples are set. So what does it mean? What is the result of it? The result of it is homogenization. And that is where part of my title is that the world is non-homogeneous, and what we are seeing nowadays is very much like a homogenization. Architecture design has been homogenized. Construction material and technologies also has a more or less similar kind of approaches, relying on cement, concrete, steel, aluminum, glass, and probably for a large part of many of the population, we really don't see why do we really need to rely on some of these construction technologies. It is important that buildings and building sector goes through the industrialization, for sure. Industrialization has given us a lot of benefits to the society, but not necessarily that industrialization has to take place with a homogenization. There could be enough variations in the approaches as well. So what has happened also, that architecture design, construction technology, construction material technologies also had led to a comfort expectations, which also is getting homogenized. The kind of set point temperatures we seek, kind of relative humidity, inside relative humidity we seek, also across the world is slowly is getting homogenized. And that has led to operational strategies, more homogeneous, and probably codes and rating programs and standards which are coming out, also probably partly pushing us towards homogenization. However, they don't give us a benefit, or they do give us a certain kind of flexibility. But what happens ultimately is that our comfort expectation, and that is where my talk is focusing on, are getting more and more homogenized. The cooling technologies, probably one or two kind of technologies nowadays we see in the world are responsible for providing cooling. Hardly, and in fact, I can say only one technology, which is vapor compression cycle-based technologies, which is, now that is primarily because we are trying to deal with a very narrow band of comfort expectations. Codes, standards, and rating programs are required. They help us to compare various kind of benchmarking. They help us to set the benchmark and then compare various buildings. They help us to normalize many of the things which we would not be able to do it. So they are essential. The methodology which we follow to derive codes and standards are extremely important. But probably the kind of values which some of these prescribe, these values needs to be questioned. The numerical values which needs to be questioned. There could be a same process, there could be a same research methodology, there could be a same way of deriving it, but probably the context under which we derive that numerical values probably is where we need to get out of this homogenization. Now that was a sort of little bit of background about what was happening in the world from architecture to probably what's happened for the thermal comfort or comfort expectations. Next few slides, I'll try to deal with what are the regional contexts, and especially in and around India, what are the kind of scenarios which we are seeing nowadays. At least India, until recently, even still today, we try to struggle to get clean air. We try to struggle to get a clean water. We also try to struggle to get a nutritious food. Although we have made a good amount of progress in achieving these basic necessities. So definitely, at least in last 50, 60 years, huge amount of change positive change we have seen. But the moment we have started gaining a little bit of, I would say, comfort zone that, oh, now probably we are getting a little bit of air, cleaner water, nutritious food. Another unique challenge which has started emerging is thermal comfort. Thermal comfort has started becoming a necessity. The way we have built in last 30, 40 years, especially in urban sector, the way we are seeing heat waves, frequent heat waves, the way certain technologies are rejecting heat all the time when you start using air conditioners inside, and the kind of materials and technology which we have used in the cities definitely has at least made cities from outside, they have made very, very uncomfortable. However, looking at indoors are getting better and better, probably without understanding what's happening outside. We get good views, good sunlight, without even recognizing that how much are we sort of pumping in to get a comfort. In India, about 1.130 million population, about 65% of that, or rather about 50% of that in an urban area, is going to be in urban area in next few years, and about 50% of that are living in a warm and humid climate. If you look at all our major cities, Calcutta, Mumbai, Chennai, and entire Western Ghats and also Eastern Shore, lot of major cities are located in this area. What this particular visual is telling us, that amount of urban sprawl we have in that climate, and about amount of people do we have in that climate. And as you can see, the warm and humid is really, really dominating the numbers. Other than, next is a composite, which is places like Delhi and Chandigarh, a little bit of north of India, and then hot and dry and cold and temperate. So large population in India is in the warm and humid part. What you see here on primary y-axis is person cooling degree days in millions. That means cooling degree day multiplied by amount of people staying in requires that amount of cooling degree day. And on y-axis, what you see, or what secondary y-axis, what you see is air conditioner ownership in residences. And you can see, last but third, India person cooling degree days in millions is sort of close to about 45 lakhs in India, what we call it, which is about 4.5 million. And household air conditioner ownership is less than 10%. As against, if you look at other similar economies, probably Indonesia, much lesser population, but probably AC penetration is also reasonably well. Versus if you look at Brazil, AC penetration is much higher. China, AC penetration is much higher. And definitely Japan and United States, looking at the economy, the air conditioning penetration is much higher. People have 3 or 4 air conditioners in their houses versus probably 0.1 or 10% of 0.1 in India per house. So that's what the context we are dealing with. And recognizing that context, India and the Indian government took a step probably about 3 years back to come up with the India Cooling Action Plan. We call it ICAP. Probably this is a very visionary document we got. Many of us contributed to that. And this is probably one of the first cooling action plan, or a national cooling action plan came out in the world. Now World Bank and many other multilateral agencies are working with other Southeast Asian countries or countries who are closer to the topic to come up with their own action plans for cooling. But this particular document at least suggests us that in next 20 years, India is going to see probably 8 times growth in its cooling demand. And building sector only is going to see probably around 11 times growth as against the baseline of 2017 and 18. And in that cooling, the large part, about 74% in next 24 years, next 20 years, is going to be a space cooling. So this is where we will be probably have about 800 million tons of space cooling in India in next 20 years or so. That is extremely large number. There's another calculation suggests that probably by 2050, amount of energy or electricity we will be using in India would be equivalent to today's generation capacity of India. And that is amount of cooling we will be requiring by next 30 years or 40 years. That's huge number. One side, we have that demand. Another side, as you know, that heat waves or extreme events regarding heat leads to economic deficit as well. And that these extreme heat events are going to go up, especially in the areas where you can see on the map. What we are going to, and this is what is been, which is a little more worrisome, is it's not just a temperature which is going to go up. It is number of humid days are also going to be more. Earlier time, just before monsoon in some of the places in India, just before monsoon, about 25 to 20 to 25 days, it used to be high humidity. And all of us are experiencing, we have numbers, that this 20, 25 days has gone up to about 45 days. So humidity and high temperature, both together is really, really driving India's cooling demand. Definitely has impact on economy and percentage of world's population which is going to remain exposed to these extreme UTR 7 days or more, as you can see on the right hand side, is probably going to be about 30% by 2050. So that's where cooling is going to grow. What you see on the left hand side is New Delhi is one of, I think this is 2018 peak load. So in winter time, we get a peak, grid peak around 9 o'clock, 10 o'clock in the morning. And then again, we peak by probably about 8 o'clock in the evening. But in the summertime, and as you can see, the deficit is huge, probably about 1,000 megawatts only in New Delhi is where we get winter time about 2 o'clock, 3 o'clock, and summertime in New Delhi. That's where the peak happens. And cooling cost as a percentage of median household income is about 10% or 11% in India, as against probably 4%, 7% in Indonesia or Brazil. So that also, when cost of getting cooling is reasonably high. And this is where we say that the India Cooling Action Plan and the subsequent work which some of us are doing, we sort of are now looking at cooling as a means to achieve certain kind of better health and better productivity as well. It is a basic necessity. It has become a basic necessity in countries like India. And if we look at what Prime Minister Lee stated in 2009, is that air conditioning was a most important invention for us. Perhaps one of the single invention of the history. It changed the nature of civilization by making development possible in tropics. With the amount of cooling and a kind of cooling which we have started using, definitely it has provided a reasonably good boost to our economic activity which we can carry out inside the buildings as well. Earlier time, probably I can imagine 1990, the kind of, there are a lot of cities, and you might have heard about this word called siesta. A lot of cities will go between 1 o'clock and 4 o'clock, 5 o'clock in a siesta mode. That means shops will get closed. That means offices, people will go back home and will rest. Primarily, one of the reasons was that it was impossible to conduct any kind of work in offices or even in retail shops. But now our shops remains open, offices work most of the time, at least 9 to or 8 to 8. In fact, India's information technology giants also started working 24 hours. That was primarily because of the access to the cooling and reliance on air conditioning. So what are we doing in terms of meeting the requirement? We are saying that cooling for all without warming the planet. How are we going to solve India's cooling dilemma? On one side, you want economic development, you want people to remain in a healthier environment, healthier indoor environment. At the same time, you have a challenge on the other side, an environmental challenge. And how do we really balance between these two? And next 2 or 3 slides, I'll try to show you what. So I did mention about India Cooling Action Plan. This is a document is now we are trying to implement whatever recommendation happened from the central level. Now each state is looking at this, and there's an organization of industry, civil society organization, and R&D organization. All of them have come together and have established something called India Cooling Coalition, and they're helping government to implement the India Cooling Action Plan. At the city level, again, one of the example, a city from where I come from, Ahmedabad, extreme heat waves is very frequent and very normal in the summer. How do we sensitize people about these heat waves? So the local government, Ahmedabad Municipal Corporation, has devised certain kind of processes by which they work with the Indian Meteorological Department, and in advance, 2 days in advance, 3 days in advance, we announce on the various social media, banners, billboards, try to sensitize people that there could be a heat wave, and there are various categories, orange, red plus, and we try to help people that how to mitigate these. Generally in Ahmedabad, our public parks, the green gardens do remain closed in afternoon times. But when this heat wave is coming, is supposed to come, probably we make sure that these gardens are open, enough water available for people to drink. And that's how local government starts dealing with a certain kind of. And on a building sector fronts, we have a National Building Code, which is again a document which everybody refers when it comes to building code, which talks about structural system services, including energy. And we have a special energy codes, energy conservation building code for commercial as well as for residential. India model for adaptive comfort was introduced as a part of these codes. That means that India, the prescription to achieve comfort or prescription to provide a set point temperature inside buildings based on adaptive thermal comfort model is now part of the national code. Probably India is one of the country where we have reasonable understanding about comfort expectation in the mixed mode buildings, and that equation is also very much part of the code. So this is how some of the work which is happening is trying to mitigate the kind of challenges which we have. When I was talking about homogenization, and I thought that probably it's important for me to also demonstrate that what are the difference in these numbers. So I have pulled out these two graphs from our earlier study, which was India model for adaptive comfort. And what you see here in black is where ASHRAE 55 adaptive thermal comfort standards numbers are. And in the blue, what you see is India-specific numbers, or India-specific, the numbers derived out of India-specific equation. And as you can see, for ASHRAE 55 and EN also, both, which are international standards, how our own adaptive thermal comfort based equation is varying. Probably Indians are more tolerant and also have a wide range of adaptation. What we believe is it's not just by coming out with the 1 or 2 research papers and coming out with these equations, which are now part of the codes. Work doesn't end there. It is very, very important that we facilitate people to practice these numbers. We facilitate people, industry and practitioners both, to help them achieve or design and operate buildings which are as per adaptive thermal comfort standard. So there are certain tools, numeric tools available which can work with your simulation tools, help you derive 30-day running mean and set point based on your climate. And also we work with the industry to come up with a certain kind of thermostat, which basically works with your existing room air conditioner, but it measures the operating temperature. One of the challenges which we have observed is that when you want to practice adaptive thermal comfort model and when your entire regime is based on operative temperature, which our room air conditioner really don't understand that. They are primarily based on air temperature sensors and basically they work there. How do we really feed the operative temperature numbers to the room air conditioner, and how do we really close the loop so that people can remain comfortable and also sort of we can start saving energy. And another work which we did with the Loughborough University Professor Malcolm Cook and Dennis Laude and his team is to come up with a ventilation guide. When outdoor is comfortable, people simply don't open the windows because they don't know whether it will help them get a thermal comfort or not. Although there are other considerations also like a noise and dust, but at least one should have an opportunity to open a window and start getting a comfort. When to open a window, how much to open a window, in what climate zone, what should be your window sizes, and what should be the operation. That the design guide is basically helping us to reach out to practitioners and help them design and operate buildings which can be a sort of mixed mode buildings. What we try to do is we try to promote a practice of design and operation of mixed mode buildings, and that's where some of these guides are extremely helpful. Demonstration of NZEBS, demonstration where the education is taking place, is also another activity which is extremely essential. I'm just showing you one example of one building which is based out of my university, based in my university, which has become a sort of learning place, which has become a demonstration. A lot of other students from other schools of architecture comes and look at this building construction. We continuously keep monitoring. This is probably the 5th year where we are monitoring and publishing the data. How are we operating this building as a net zero? And it takes a while for some part of the industry to understand numbers. Generally, there would be a little bit of pushback comes from one sector of a design team. No, we don't understand numbers. It is important that we start communicating that. We start showing them that how the buildings are getting operated. When you open a window, what happens? When you close window, what happens? And when you start relying on some of the technologies which are not being tested, for example, many of these earth blocks or earth bombs or laterite blocks, which may have enough to offer us to design and operate buildings in a mixed mode operation. That's where we also try to look at some of these examples. And finally, this is a last few slides where I'll try to expose you with a kind of very ambitious project which we are part of, is the Global Cooling Prize. And what you see on the left-hand side is a theoretical efficiency which has been achieved in LED lighting. In a retail is about 67% efficiency has been achieved, and another 22% is in R&D. So probably we can say that in next 7, 8, 10 years, we will be able to achieve probably close to about 90% efficiency when it comes to LED lighting, a theoretical efficiency. When it comes to a solar photovoltaic, again, about 50% we will be able to achieve. But somehow, room air conditioner, since last about 100 years or at least 80 years, we have not moved forward. About 7 or 8% in 1930, what we have achieved so far is just about 14%. And there is some reason behind this. The reason is that very few companies do produce a room air conditioner. So market has a huge inertia. Very few companies those who try to come up with a new technology do not get a space because these giants exist in the world. So the Global Cooling Prize is trying to attack that. We have floated this competition. We are sort of halfway, where what we seek is 5 times less climate impact from a room air conditioner, which can be used in a residential environment. So there are 2 key parameters by which we are going to evaluate. One is the climate, which is 1/5 of lifetime climate impact. And second is affordability. It has to be affordable if you produce about 100,000. And then we are also trying to look at the power requirement and water, trying to manage that. We don't want to solve one problem and come up with another problem of water or power or whatever. And these technologies are going to be tested. One of the rigorous test protocol we have derived, and it's going to be tested in a site, in a field simultaneously, and also in a lab which is located in my university. What happened in last about 1 year, about 2,100 plus team registered for this competition. About 500 of them completed their intent to apply. About 140 came up with the detailed specifications and design, and from 31 countries. These 140 or 139 applications were checked thoroughly inside out, including the quantity of bill of quantities and so on and so forth. And we announced about 8 finalists who will go in the next round last year. These 8 finalists again shows a diversity. There's some giants like Daikin and Gree were part of it. Some startup from university like Barakol, and some other startups like Creton and SNS Group, which are not part of the university but are still competing. And all these 8 do show us a diversity in a technology by which they are trying to attack the cooling. The diversity in a profile of these companies, and also some of them are from China, some of them are on India, some of American, and also British and Japanese. Their approach, these are the sort of high-level summary of these the finalists. They are trying to deal with a very degree of global warming potential refrigerant. Many of them are trying to segregate sensible cooling and latent cooling. And some of them are also trying to hybridize some of these technologies. So what this shows you is a variation in an approach which these people are adopting. Some of them also have integrated photovoltaic on that. What would be the impact of that? What you see in a red is sort of reference scenario or business as usual room air conditioner growth, where current adoption or committed policies will take us to. The gray which you see is where the impact of Kigali is going to be. That if same reference scenario, but adding all successful implementation under Kigali phase down plan, what you will get is probably what you see in a gray. But a 5 times less scenario is what you see about 65% below the Kigali phase down plan, which will result into about 75 gigatons of carbon emission avoided through 2050. And if we get success, if all these technologies, not just a winner, but all these technologies which are getting developed, if they start getting into practice, we will be sort of close to about 0.5 degree global warming mitigation by 2100. Last few slides. Building performance simulation without confirmation bias. One of what I feel is that BPS is one of the most promising approach to design and operate buildings and cities. And that is where the importance of BPS community is. But there are a few questions on that. Do we have enough practitioners? I know a lot of universities are doing cutting edge research, really training people for good BPS practice. But have we really translated this R&D and education into practice? Do we have enough case studies to show to our students? Do we have a permanent seat in a design team like a structural engineer? No architect will design building without structural engineer. We need to reach to a place where no building design takes place without going through the BPS rigor. Is BPS practice led only by codes and rating programs? And that is what unfortunate condition right now is, which is partially, it's good that at least something is happening. But what we really need to do is that probably we just don't need to use BPS to comply codes and rating programs. We need to really push BPS to the level where we really design almost all major buildings through the BPS board, and we can lead the design and operation building of buildings through BPS. is what my question is, that does BPS has enough to offer to the world, to non-homogeneous world? Do we have enough people who can simulate looking at adaptive thermal comfort standards where you have a varied set point based on 30-day running mean? Will your HVAC system will respond to that? Do we have enough people in practice? Definitely not in education, not in R&D. Do we have enough people who can really simulate thermal mass effect extremely well? Do we have enough people to do a natural ventilation modeling? There are an extremely good example, but probably I would like to put them on an elite platform. No doubt, natural ventilation simulation through CFD and many other means are doing really, really good work. But are we making them a mainstream? That's where we are right now. Are we really addressing the requirement of non-homogeneous work? Thank you.
Thank you very much. That was a really great presentation. And you touched on a lot of really important topics. I want to give the audience a chance to ask any questions now. So you can ask questions via the Q&A platform, or you can raise your hand if you'd like to give a verbal question. So either way, just let us know. And it seems like we have already a question from Malcolm Cook. So how closely do services engineers and architects in India work together?
Less than 0.001%. Very few will bring the service engineer on board from early stage of design. The reason of that, also I will put a bit of onus on approach we as an architect has, is that, and not only architects, but largely the society has adopted this approach, is a technology fix. That you do whatever you want to do, finally there would be some technology who will bail us out. And that's what probably the approach some of the architects are also, or I would say mainstream architects also has, that you start designing whatever way you want to design it. There would be a structural engineer who will come and help you out to build it. And there would be a service engineer who will come and help you to make people comfortable inside. But you don't really realize that what does it take in terms of environmental impact to make people comfortable. So there is a bit of technology fixed approach in some of the practitioners, and hence they don't bring a technical manpower, technical mind early stage in a design. I hope that answers Professor Cook's question.
Yeah, I think that was a good answer. I had one last question. So you talked about many different strategies for how to address this cooling challenge. So what are the key elements you think that are necessary to deliver cooling for all without warming the planet?
I think the first and foremost is downsizing of cooling requirement through the building envelope design. That's where the basics are. And once we do that, once we have a sensible design which can downsize the requirement of cooling, and that's where we talk about mixed mode buildings, then we need to look at how do we really separate out the sensible loads and cooling loads and start dealing with that. And third would be controls and communication and operation. How smartly we start operating these three together. So first is downsizing, surely. Second is cooling and separating out the sensible and cooling load. And at least if we can do this too, we will be able to provide thermal comfort for a large part of this population in near to tropics.
Great, thank you. And we have another question by Rebecca Ward. Is there potential for retrofitting any of the technologies being developed?
In terms of technologies which are vapor compression cycle-based technologies, I see a very less possibility of retrofitting them. At the most, what you can retrofit is with a little bit of controls and a little bit of IT into it. But core technology itself really cannot be changed. If your question is pertaining to buildings, I would say there is a huge requirement and possibility of doing building retrofits in a various manners. Right now, when we see building retrofits, it's just insulation here and there and some window change and stuff like that. But probably we might require much more thinking when we want to do building retrofits in a more diverse fashion.
Thank you. Let's see. Do we have any more questions from the audience? I know we are at the time for the session. So with that, I'd like to thank you very much. I wish I could get a whole round of applause from the audience, but it's been a great talk, and thank you very much. And I guess I'll see you in person soon.
Sure. Thank you very much for inviting me, and my regards to all of you. Have a great day. Have a great conference. Thank you.